Alright, so let's do some simple harmonic motion problems, and specifically we're going to be doing periodic motion, and we're going to be using penduli and springs as an example. So, for problem 1, I'm not sure if you can read this, so I'll go ahead and read it off to you. Problem 1. After landing on an unfamiliar planet, a space explorer constructs a simple pendulum of length 55 centimeters, or that's also 0.55 meters. She finds that the pendulum makes 90 complete swings in a time of 145 seconds. So, the variables we're going to have to know for a pendulum are the period, the length of the pendulum, and the acceleration due to gravity. And the formula that we're going to be using is that the period equals 2 pi, which is one full circle expressed in radians, times the square root of the length of the pendulum divided by the gravity. So, we know that the length of the pendulum is 0.55 meters. And the reason I'm doing this in meters and not centimeters is because then it's going to be much easier to express gravity, and we won't have to make that conversion later. And then, so this is going to be our unknown, and then we know that it makes 90 complete swings in 145 seconds. So to find how long it's going to take it to complete a swing, we're going to have 145 seconds divided by 90. And then when we plug that into a calculator, we get that it is 1.61 repeating seconds per swing. So now that we know almost everything, except for gravity, we're just going to plug this all into the equation. Let me just erase this to make some room. Alright, so we're going to have RT, which is 1.6 seconds. So we're going to have 1.61 bard is going to equal 2 pi times the root of 0.55 meters divided by the acceleration due to gravity. And now the reason that we don't care about mass is that it's going to be effectively the same thing for any sort of mass that we use on the pendulum. So we're going to first want to isolate our variable. So the way we're going to do that is we're going to have 1.61 bard over 2 pi is going to equal the root of 0.55 m over g. Now we're going to square both sides. So we're going to have 1.61 bard over 2 pi quantity squared equals 0.55 over g. So then we're just going to multiply both sides by g and divide both sides by this. So let me make some room up top again. So then we're going to get that gravity is going to equal 0.55 over 1.61 bard over 2 pi squared. So first I'm going to simplify this term. So we're going to have 1.61 bard, and we're just going to divide that by 2. I'm going to do 2 times pi, and square that. So we're going to get that the acceleration to gravity is 0.55 over 0.06574 dot dot dot. Then we're going to divide 0.55 by that number, and we're going to get that the acceleration due to gravity is 8.365105,843 meters per second per second. So that's how you'd solve the problem. Just want to find whatever variables you can and get into the equation. So I'm going to do one more problem, and this one's going to be a spring problem. As in the object, not the season. Alright, so the problem reads: a massless spring with spring constant 21.6 Newton meters hangs vertically. A body of mass 0.230 kilograms is attached to its free end and then released. Assume that the spring was unstretched before the body was released. What is the frequency of oscillation of the resulting motion, assumed to be simple harmonic? So the equation we're going to use is that the period is going to equal 2 pi times the mass over the spring constant. And the reason we use mass in this and not gravity is because the force that is going to be applied on the spring is going to be different for each mass because it's being accelerated by gravity at a different rate, and we're not caring about how fast the mass is moving, but with what force for the spring. That's why we're using the spring constant. Alright, so for this, we know that our T is what we don't know. We know that our mass is 0.23 kilograms, and we know that our spring constant is going to be 21.6 newtons per meter. Alright, so when we're going to plug this into our equation, we're going to get T equals, this would be the root. T equals 2 pi times the root of 0.23 for 21.6. 2 pi. Let's simplify this term. 0.23 divided by 21.6. Take the root of that. We're going to get 0.10318 dot dot dot. Then multiply that by 2 pi. We're going to get that the period equals 0.64836100394. So that is how long it takes for one cycle to complete. So now we know all of our variables, so I'm just going to go ahead and erase this. But, okay, so what the problem's asking for is frequency. What is the frequency of oscillation of the resulting motion? Now, let's say that the frequency, well, actually it's in hertz, is equal to 1 over the period. It's just, they're inversely proportionate. So, we know our frequency in hertz is going to be equal to 1 over 0.64836100394. So let's go ahead and divide 1 by that, and we get that. Our frequency is going to be 1.542350541. And so that is how you would solve that problem. Again, it's just finding whatever variables you can, plugging it in using that equation. So, cool.